Welcome you all to the new lecture video on electrochemistry. Electrochemistry is basically an applied field of chemistry. It has various applications in distinct areas of everyday use. Just like in metallurgy, in chemical industries, in paint industries, and obviously in battery industries. We know all about the presently discovered lithium-ion battery, etc. In the part 1 of the lecture series, we will discuss mainly on electrolyte solutions, Debye and Huckel theory, and activity coefficients. Now, previously we have learned about ideal and non-ideal solutions, or basically non-electrolytes. And we know that a non-electrolyte solute can behave as ideal solute. That means it can obey Henry's law at very dilute solutions. These types of solutions is called ideally dilute solution. So in ideally dilute solution, non-electrolyte solute obeys Henry's law, and the solvent obviously follows Raoult's law. So an ideally dilute solution behaves like an ideal one, and we know that the chemical potential of the solution, rather chemical potential of the ice species in solution, mu y, we can write it as is a function of temperature, pressure and mole fraction of the solute, is equal to the standard chemical potential mu y 0 Tp plus RT ln xi. And ideally dilute solution means xi tends to 0. Solute concentration is near about 0. But if the solution is not an ideal one, it's a non-ideal solution. If it is a non-ideal solution, so we can modify the equation for non-ideal solution. We can modify the equation as mu I Tp and mole fraction should be replaced by activity. So we can write it Tpai is equal to mu I 0 Tp plus RT ln AI, where AI is the activity of the ice species. And we know that this AI activity, AI is related to the mole fraction through the activity coefficient. We can write it as gamma I into xi, where gamma I is the activity coefficient. Activity coefficient. It's a measurement of the non-ideality of the solution. Now, in the vicinity of xi tends to 0, gamma I tends to 1. So, in a very low concentration of the solute, almost 0 concentration, this equation converts to the previous equation. That means the equation corresponding to an ideally dilute solution. So this is all about non-electrolyte solute. Now this mole fraction unit can be replaced by other unit also. We can write it in molar concentration term. The equation will be converted in molar concentration. In molar concentration, we can write the equation as mu I Tp mi, this is the molality of the I species, is mu I 0 Tp plus RT ln ai, that means mi into gamma I. So this will become mu I 0 Tp plus RT ln mi plus RT ln gamma I. Now sometimes this term mi, this is the molality of the I species, but we know any parameters that is in logarithm term, it should be dimensionless. So sometimes it should be written in a proper term RT ln mi by mi 0 plus RT ln gamma I for a non-ideal solution. mi0 is just 1 mole per kg. 1 mole per kg. So these two equations are similar, but to be written in a dimensionally correct form, it should be written in this way: mu I 0 Tp plus RT ln mi by mi0 plus RT ln gamma I. So how activity coefficient is related to the chemical potential of the species, that can be represented by this equation. But all those equations are related to the non-electrolyte solution. So the summary of the discussed topic so far is that a non-electrolyte solute can behave like an ideal one at very dilute concentration, but that is not the case for an electrolyte solute. So if you have an electrolyte solution, you cannot have an ideal solution if in the solute concentration is very, very low. So our discussion is mainly about solution of electrolytes. So there is a difference between the solution of there's a difference of treating a solution of non-electrolyte and a solution of electrolyte. Thus a very dilute solution of electrolyte behaves non-ideally. It is due to the long-range Coulombic interaction between the ions. So non-ideality exists even at very low concentration of the electrolyte solute. Now Debye and Huckel proposes a theory for calculating the deviation from ideality, that means the activity coefficient. For dilute solution of electrolytes, they proposes, or rather they assume, that all the deviation from Henry's law behavior arises due to Coulomb's interaction among the ions. According to Debye and Huckel, a central ion is surrounded by a charged cloud atmosphere of opposite ions. Suppose there is a positive charge at the centers with charge Z plus C, and now around the positive ions there is a net negative charge cloud of charge Z minus C. In this region there is obviously also some positive charges, but the overall charges is negative. Just like here, this is the central positive ions, and in electrolyte solution an air atmosphere forms where mostly negative ions surrounds the positive ions. This temporary arrangement is called ion atmosphere. Beyond that region, because in that region there is electroneutrality, that means equal number of positive and negative ions. But within the air atmosphere, if the central ion is a positive one, there is a conglomeration of net negative ions. Similarly, if we have a central negative ions, then a positively charged clouds surround it with net positive charge Z plus E. Thus, a central ion of Z plus E charge is enveloped or surrounded by a charge cloud atmosphere or total charge minus Zi. Thus, the central ion of Zi charge, this means plus charge, is enveloped by a charge cloud atmosphere of total charge minus Zi. So this is the ion atmosphere concept of Debye and Huckel. Now, Debye and Huckel successfully calculated the time average spatial distribution of excess charge density around a central or reference ion. Why it is time average? Because these ions, this ion atmosphere is not a fixed, is a temporary arrangement. Ions are dynamic in solutions, so number of positive ions and negative ions changes within a vicinity, but at any time surrounding a positive ions, there is a net negative charge of negative charges ions. So let's imagine all the ions in the very dilute solution are discharged. That means if the electrolyte solution are assumed to be neutral, then no Coulombic interaction there, and it shows an ideally dilute behavior. And we know in ideally dilute solution, the solutes obeys Henry's law, and we can write mu I ideally dilute is mu I 0 plus RTL and Mi. Already mentioned it we have. But actually the electrolyte solution is not a discharged solution. The ions have charged, so chemical potential in the real solution mu I real is mu I 0 will be mu I 0 plus RTL and Mi gamma I. We have already mentioned previously, gamma is the activity coefficient. So what is the change in chemical potential? That means Gibbs free energy per mole is mu I real minus mu ideally dilute is equal to RTL and gamma I. So this equation will give us the value of gamma I, activity coefficient. This chemical potential arises, the change in chemical potential del mu arises due to ion-ion interaction. So calculation of del mu may lead to the estimation of gamma I. And Debye and Huckel, they have successfully calculated del mu, and from that they have estimated gamma I for an electrolyte solution. Now, we first calculate work done to charge a discharge ion from 0 to Zi charge, because we have initially assumed that the electrolyte solution is discharge one. That means it has no charges. It behaves like an ideally dilute solution. It obeys Henry's law. Now if we want to charge it, what will be the work done? Because we know that del mu, it is related to the work done, because non-mechanical work done is related to the Gibbs free energy change, and Gibbs free energy change per mole is related to the chemical potential. So if we can calculate the work done for charging a ion from 0 to Zi charge, then it will be the del mu for that process. Now from classical electrostatics, now you understand it from classical electrostatics concept, that potential at the surface of an isolated conducting sphere of radius A. Suppose we have a conducting sphere of radius A, and that is immersed in a dielectric medium of epsilon. Epsilon is the permittivity, and epsilon is related to epsilon 0 into epsilon r. Epsilon 0 is the vacuum permittivity, and epsilon r is the relative permittivity of the medium. So according to classical electrostatics, the electrostatics potential at the surface of radius A, phi A is equal to Q is the charge by 4 pi epsilon A. Now if we want to charge the sphere, then the work done will be simply phi a into dq. It will be integrated from 0 to q, and ultimately it will lead to half q into phi of a. This is the half of q means the charge, and this is the phi a, the electrostatic potential. So this is the case for an conducting sphere, but we don't have any conducting sphere. We are dealing with ions. So if we want to charge an ion from 0 to ZIE, similarly we can obtain the work done W. This is work done per mole, so that's why Avogadro number is multiplied here. So Na into half into Q. Q means ZIE, and the electrostatic potential will be ZIE by 4 pi epsilon Ri. So this is the work done to charge an ion from 0 to ZIE charge. But this is the chemical potential, or rather work done, in the absence of any ion atmosphere around the ion. So if there is no ion atmosphere surrounding an ion, a reference ion, then its electrostatic potential will be ZIE by 4 pi epsilon Ri, this one. But we know, according to Debye and Huckel, every ion, whether it is positive or negative ions, it is surrounded by an ion atmosphere of opposite charges. So there is an ion atmosphere of opposite charge near the reference ions, and this cloud atmosphere reduces the electrostatic potential at the surface of the central ion. So actual potential will not be ZIE by 4 pi epsilon Ri. The potential experienced by the ions will be little bit less, and that will be ZIE by 4 pi epsilon Ri minus ZIE chi by 4 pi epsilon, where chi inverse reciprocal is the thickness of the atmosphere. We'll come to these parameters later on, and it is called the Debye length. Also, the electrostatic potential of the ion atmosphere, that is phi cloud, is minus ZIE chi by 4 pi epsilon. How it comes, we'll come to it in our later video. So now the overall del mu will be W is equal to the non-mechanical work done, this means electrical work done. Change in chemical potential is equal to the non-mechanical work done, is equal to Na. This is the Avogadro number. This is work done per mole plus into half into charge of central ion. Central ion charge is just ZIE, and phi into phi of cloud, and phi of cloud is already is minus ZIE chi by 4 pi epsilon. This gives this equation. So we have a expression for mu, or rather del mu, and we can relate it to the RTL and gamma I. Now as a continuation of this video, we'll come up with one more video, how this term, this phi cloud, arises or appears, and what is the significance and expression of chi.